Okay, welcome back to this second online session of this course, Nuclear and Particle Physics. Um, so I will take up if there are any specific queries, but let me just briefly give you some kind of a flavor of what would be the um, motivation to actually look at the details of particle dynamics in the context of the universe. So what we know somewhat fairly well is that the contents in the particle in the universe, all the matter content in the universe is kind of made of smaller units. And presently we believe that we can bring that down, that basic building blocks of all these structures around us, including the terrestrial structures and then the um, stars, galaxies, and other heavenly bodies, and everything that we see in the universe. In the, I mean, are we can imagine them are made of elementary particles like electrons and protons and neutrons, etc. So from this point of view, we can ask the question like maybe how all these structures evolved in the universe. So there we also need the picture of the universe put in the context of the gravitational interactions and how the universe must have originated and how it may have evolved over time. So again, we have relied on observations as in any other physics studies. So our observations of the universe, different objects that we have in the universe, and various other observations related to the what is called the cosmic microwave background radiation, etc. And more recently, the gravitational waves and such observations all lead to very convincing possibility of the universe starting with a very high temperature, high density state, and then as the time evolves, it expands, and as it expands, the density comes down and the temperature goes down, and various different structures evolve in that. How does it happen is somewhat heuristically we can imagine, like in the beginning there were kind of all electrons, quarks. Quarks are basically, we discussed earlier, quarks are the ones that make the proton and neutron. Now we can think about a state of the universe where we didn't have large structures, atoms, or even nucleus, but we had the further elementary constituents of all these structures, like quarks and electrons. Maybe there were also electron-like other particles, and then there were also photons, energy in the form of radiation. This is a kind of a picture that we can imagine as to be there in the high dense region and high temperature. And then at some point, I mean, as it evolved, it cooled down, and then at some point the temperature was sufficiently small, or the energies of these particles, kinetic energies of the particles, were sufficiently small for them to interact effectively. And when they interact with each other and then form bound states. So that way we can imagine as the protons were formed, then further protons and neutrons, etc. As it cooled down again to below, say, or around MeV scales, they would have had enough possibility or interaction cross-section to actually um, form bound states like a nucleus. And then these nucleus and electrons would be just in a kind of moving around in a ions and electron state, which we call kind of a plasma, the usual electromagnetic plasma. And again, as as it cools down, or as the universe expands further and cools down, then we have the situation where energies of these protons and electron etc. are in the MeV. From the MeV scale to it can come down to electron volt energy scales. And when it is electron volt energy scales, then that is kind of atomic energy scales that we have, and it is possible for the electron to bound with the protons and then form atoms. So there would be all background photons in all these things. The energy of the photon should also be similar to that. You see, if we imagine that the temperature is all the same for all particles say. So it means that the photons will have less energy compared to what is needed for the electron to be ejected from atoms. So that is the stage at which atoms can be formed, and from then on, these atoms will not really interact very much with the photons, and that is photon that we call the primordial photon or the cosmic microwave background radiation. And that's what is being detected. And as it is expected, because the universe is homogeneous and isotropic in the sense that it doesn't matter where you are looking at, which place you are actually considering, or which direction you are looking at it, it looks the same. Presently, it is statement about large scales of the universe. So if you look at small scales like terrestrial scale or solar systems, the scale of the solar system or even the galactic scales, it's not uniform. If you look at in one direction, you will see the sun that is not there in another direction. That is not the meaning of isotropic, the statement of as isotropic in the context of cosmology. Basically, what it says is that apart from these local anisotropies or local differences, if you look at large distances, then everything looks the same, which means then immediately that there must be many such solar system kind of a thing or galaxies that we have in all direction, in whichever direction you look at it, which is observationally now kind of verified. And in a similar way, all this cosmic microwave background radiation is also expected to be isotropic and homogeneous. So the isotropy can be verified when is observationally seen by looking at the entire sky in all directions, and then we, by and large, we have the um, uniform kind of a distribution of the or uniform or uh, radiation that is in irrespective of which direction you look at. And now, yeah, so this is the kind of evolution of the universe that we can imagine. And this is the picture that what is called the Big Bang cosmology presents us. So it is depicted, whatever I narrated just now is kind of depicted in this slide. We can imagine different stages of the universe, different epochs of the universe. And initially it was high density quarks and electron, etc., and gluons and photons. And then it cools down to basically neutrons, protons, and the electrons, etc. And these neutrons, protons will combine together to form nucleus. So light nuclei were formed in that way. And further on, the atoms were formed and the cosmic microwave background radiation can be imagined to be there. And that is one of the basic important experimental observation that convinces or that establishes or gives big support to this Big Bang cosmology. So, particle physics as such plays a big role in this in this uh, and the whatever we have been discussing in the course, or at least part of which we are discussing in the course, are all, I mean, in fact, all of it, are important for the early time cosmology. For example, the dynamics of the nuclear physics of the light elements, because it is the light elements which are formed in this early stages of the universe, and that is very important. What is the dynamics, how that what are the rules of the game, how the nuclei are formed, how they combine or we interact with each other, etc., are all very important when it comes to the that the dynamics of the universe at this stage, which we call the basic nucleosynthesis, the era of nucleosynthesis, where the light nuclei were formed. And that is one of the things. And particle physics interactions, in terms of interactions of the elementary particles like quarks, electrons, etc., come a little before that, before the Big Bang nucleosynthesis. And that is the time where all the elementary particles are in a kind of a soup of quarks and leptons, and maybe some other elementary particles as well, and photons and gluons, etc. So that is a stage where the elementary particles are dynamics is going to play a big role or important, become important. Now, part of the course in the beginning, we in the first half kind of we discussed this nuclear physics, and then now we are actually discussing the particle physics in that. So we are currently discussing the electron interacting with itself or quark interactions, and we will also mention what is called the standard model of particle physics. So the standard model of particle physics, we will not have time to go into the details of that. Therefore, I will mention a few things in this lecture, in this discussion. So basically, the standard model of particle physics talks about the rules of, or what is the dynamics of interaction of the elementary particles, and there are particular specific rules set in considering what is called the gauge symmetry of the system, and under uh, which guides what are the different interactions that we can possibly have, what are the elementary particles that we have, how should they interact with each other, etc. One of the things that again a little bit we discuss in the course is the experimental tests of all these theoretical models. For example, the standard model is something which is very precisely tested, very, I mean, very stringently tested in a sense. And the measurements that we have of various different processes, various different possibilities that the standard model actually I mean, uh, puts forward are all tested very well. And surprisingly, although there are many different kind of independent and many different tests that one can make. For example, there are electrons and photons. So electron photon interaction, electron muon interaction, electron, or when it comes to W bosons, which are one of the weak bosons, and their existence, their discovery, and their interaction with the electrons, their interaction with quarks. All these things are very precisely measured. Small differences in their interaction, for example, how the quark interacts with the W boson, how the electron with interact with the W boson are slightly different, and they are all measured in different processes or experimentally probed in various different independent processes, independent measurements. And surprising fact is that so far we have not found much in contradiction with this one. There is one thing which, at the same time, there are a few things which are not really incorporated in the standard model, and that has its own reasons. One of the things that is not incorporated in the standard model is the presence of light right-handed neutrino. This is because of some historical reason, in a sense, that we did not really think about, or think about in the sense that we did not include them in the first place, because experimentally we had not seen any right-handed neutrino. So there was no reason to include them in the interaction, and that if we included that in the standard model, it was very difficult to imagine how can they be not seen. So the way that we had actually built the standard model is to say that there are no right-handed neutrinos, therefore light neutrinos. Now, light neutrinos are the ones that basically appear in beta decay, for example. In fact, the beta decay is the one where it was proposed, and then in a theoretically compelling, convincing reason was put forward by the Wolfgang Pauli, and it was kind of accepted by others as a reasonable thing to have the presence of a light neutral fermionic particle. So that is basically the neutron that we got. Subsequently, it was seen that it is all these particles which are coming out in the beta decay. If they are not firstly seen, directly detected, but the missing part when they analyze it through the behavior of the electrons and the nucleus that is finally there observed, it was clear that it has to be a fermion, and it has to be an massive massless particle, almost massless particle, and consistent with zero for all reasons. I mean, all measurements that we could do at that time in beta decay. So it was proposed that the neutrinos are, and also the spin alignment is such that their spin is always opposite to that of the direction of motion. So they are fermion spin half particles like electron, but the electron can have a spin in two different orientations along the momentum or opposite to that. Whereas for neutrinos, it was seen that it is always opposite to the momentum direction, and that has its own implications. And one of the thing is that it cannot have a mass in the usual Dirac sense. Now, that being so was the case for a long time, but then a lot of experiments focusing on understanding the neutrinos and its behavior, its dynamics was being proposed. For example, one of the experiments, one of the places that the neutrinos are produced apart from any terrestrial human-made experiments are is the interior of sun. Wherever there is a nuclear reaction, it is possible to have neutrinos present there. So that is so with sun as well. So the neutrinos produced in the nuclear reactions inside stars, especially sun, could be actually could propagate down to Earth. And then if we place our detectors, we may be able to catch that. This was one of the ideas. And indeed, we made appropriate detectors, which had to be very large in volume because these particles interaction with the neutrinos interaction with matter is so feeble that the probability is very small. So now you know what we do when the probability for any occurrence, any event to occur is very small. What you do is to have many events to suppose any reaction or something have many different possibilities, and one of the possibilities outcomes has a probability of 10 power minus 4 or 5. What if you want to observe even a single event, you need to have something like 10 power 4 total events. So out of the 10 power 4 total events, there will be one event of this particular kind. That is what the statistics tells us. So if there are many neutrinos which are going through us or through some detector, and if the interaction probability is very small, then possibility to see that reaction can be increased by adding volume to the detector or the detector elements. The detector volume means that we are actually adding the target number density. The target number density will actually be very large, and therefore the probability multiplied by that number density in a sense will actually give you some reasonable number, which would be the total number that we could observe. So this is the philosophy with which huge neutrino detectors were produced, built. And I don't want to get into the details of that, but basically anybody who is interested can actually look at neutrino experiments. One of these experiments had been in the Japan, KEK, Super Kamio Kande, you can see. You can search for it. Then there were all other experiments, including experiments in the southern pole, Antarctica, where we have what is called the ice cube experiments, which is looking at neutrinos coming from not sun, but from other galactic structures. This is being run, and then what happened in the solar neutrino observation, where detectors were specifically looking at the neutrinos coming from sun, and that what are there is a standard solar model which is reasonably tested in the astrophysical sense, and we are convinced about the accuracy of the model. And with that model, we can actually calculate the number of neutrinos that are coming out of solar sun. That means that we can actually check, given that these many neutrinos are coming, whether how many can be detected at these detectors. When you do this calculation at the superatomic context, say for example, and when we actually look at the result, we see that what is there is a huge discrepancy between what is expected and what is actually detected. So it's almost 50% less. That is only half of what is expected is actually observed. So now this what we are detecting is specifically electron. There are three different types of neutrinos, and the neutrinos of electron type, which is there in the beta decay. Then there are neutrinos which interact with muon, which are called muon decay, and similarly tau neutrinos. These are the three different type of neutrinos which the standard model prescribes. And the explanation for the reduction in the number density of the neutrinos coming from sun is that if it has some small mass, if the neutrinos have some small mass, it's possible that when electron type neutrinos are produced in sun and then flying off sun and then coming to earth, towards Earth. In this, as it traverses this distance, this neutrino, which is now electron type, can actually convert itself into a muon type of neutrino or a tau type of neutrino. And since our detectors are sensitive to electron type neutrino, that will not detect the muon neutrinos or tau neutrinos. So it is possible now to imagine that half of the or 50% of the neutrinos starting from sun do not reach Earth as electron type neutrino, but as muon type neutrino, and we don't see that. So this explanation was kind of is reasonable. And then there are further details of the experiments, etc., as to be considered. And then it is now convinced, we are now convinced that this oscillation, neutrino oscillation, is a reality. Now, if the neutrino oscillation need to happen, then the neutrino has to have some mass. Meaning, if it was strictly massless, which means that the mass of the neutrino was identically zero, then we will not be able to have the change in the type of the neutrino from electron to neutrino, muon. That's possible specifically because of the mass, and mass eigenstate being a mixture of both neutrino, electron neutrino and muon neutrino. So that is how it goes. And this is kind of now accepted as the real thing, what is actually happening. And in a similar way, other contexts also, it's not that we just are satisfied with an explanation and a particular experiment and its outcome. We want to actually convince ourselves in a more in a deeper sense, and also we want to find out if there are any details that are missing. So for that, we keep doing experiments otherwise. So there had been also other terrestrial experiments where neutrinos produced in reactors, like any nuclear radiation can also potentially have neutrinos, and then there could also be other um, possibilities of generating neutrinos. Say, for example, these mesons that we talked about at some point, pi meson can decay to neutrinos, electrons and neutrinos. You can actually arrange the things so that we can have a beam of neutrinos also. And now we are actually capable of performing experiments with this neutrino beams also. So there are various different type of these experiments, different locations, entirely different experiments which are completely independent of each other are all performed. And then now everything is consistent with the explanation that the neutrino oscillation is a reality, that the electron type neutrino can convert itself into a muon type neutrino as time evolves, as it propagates through that space. So these are the things that actually not possible to be included in the standard model. As I said, neutrino is strictly massless and then strictly left-handed alone in the standard model. So this disallows the mass, non-zero mass. And now that we know that it can have small mass, we have to modify the standard model a little bit to include the neutrino mass of the neutrino as well. So this is something which we are still developing in a. There are a lot of important and interesting proposals and models which are tested very well, proposals which are realistic possibly, and but there are aspects of that which are not experimentally tested. So in that sense, it is still a model which require confirmation. And there are multiple possibilities, not one single possibility. There are many different ways that small neutrino mass can be generated. And we have different experimental sensitivities for these different possibilities. So all these are being tested at the moment. And then we have this neutrino um, the studies of the neutrino. In the global context of particle physics is one of the major studies at the moment. Then there are other things like the dark matter and dark energy, etc., which are also very important. So the dark matter itself is one of the results of a detailed study of cosmic microwave background radiation. Well, dark matter had been proposed long before, even otherwise, before even detecting or proposing the possible cosmic microwave background radiation. The presence of some large amount of mass beyond what the luminous mass in the galactic center that is seen by observations uh, was proposed long before. Various reasons are there. So one of the reasons is that the rotation curve of the of the stars in the outer regions of particular galaxy, many galaxies or galactic clusters are seen to behave differently compared to what the Newtonian mechanics would predict, considering the visible matter in that galaxy. So when we talk about, say, a galaxy or a star or anything, we also talk about the mass of that object. So mass of these objects are determined from the luminosity of that. And this means that it is basically the usual matter that we are considering, which can emit radiation, interact in an electromagnetic way, in the usual way that we know. But there are also, that way of estimating the mass is pretty accurate. And what is seen is the velocity of the or the speed of the stars in the outer regions of any galaxy that we consider. We see the speed much larger than what is expected from the Newtonian dynamics, Newtonian gravity, if the visible matter is the only thing that is available and is focused and concentrated at the center of this. And one explanation to this is that in addition to this visible matter, there is some large amount of additional matter that could be spread out in a way in the galaxy, and but we don't see it. So this is kind of termed as dark matter. Now that's one possible explanation of this. There are other explanations of, say, for example, why don't you modify gravity, Newtonian gravity, to suit the observation? That is a possibility, but this is only one observation. One observation meaning one type of evidence for presence of, or evidence that needs either relook into the Newtonian dynamics or consider that the visible matter is not enough. But there were also other examples and other places, completely different type of behavior, different places, different observations, where again the presence of large dark matter, kind of matter that is not visible, the matter that cannot emit large amount of radiation, like the normal matter. Normal atoms emit radiation, but there could be particles which are different compared to these normal atoms, which do not have radiation, do not interact electromagnetically. So that proposal could actually explain many other anomalies otherwise seen, including what is called the gravitational lensing and etc. But in a global sense across the universe, in a cosmological sense, the measurement of this and the existence of dark matter and quantitative estimate of the amount of dark matter in the universe is given by observation in the detailed observation of the cosmic microwave background radiation. So I don't want to go into the details again. If anybody is interested, we can discuss that. But essentially, it says that the amount of dark matter that is present in the universe compared to the usual normal matter is very large. So if the considering the total energy content of the universe is 100, so the 32 percentage of the matter is dark is matter, and out of this 32 percentage of matter, so of I mean we have only 5% as the normal visible matter which interacts with photons or which can emit radiation, etc., which are the normal matter, making atoms and other these things. But the rest, that is about 27 percentage, is this dark matter, which interact very weakly with the normal matter, etc. And now this is another area which is very active in terms of research. And the point that particle physicists have been exploring and trying to understand is what kind of elementary particle can give rise to this? What are the different properties of this? And what should be the amount of interaction that is allowed or that this can have with the standard model? Or are there different such element dark matter particles? If that is there, then how do they interact with each other? How much of each different type will be there, and things like that are this very active area of research now. Okay, so these are some of the interesting things that is very closely related to the course that we are having now, but slightly beyond the discussions that we could have here. But once you have a good understanding of these elementary dynamics, it will be easy for you to uh, um, understand all these other dynamics that we have, including that of the dark matter, etc. Okay, so I think I will kind of stop here, and I hope the course is going on well. I don't see much of the discussion here. And if there are any questions, then I will be happy to take that. Hi. Alice? Huh? Camera. Okay. So I don't see any questions as such. So should we stop or? Okay.